Okay, so this is just a short additional video to week 12 in review. It's a bit of a standalone topic, and it was introduced to the level 3 course this year, which is on the concept of entropy. And entropy is a measure of how much disorder there is in a system, and we're talking about disorder of particles here. So I'm just going to go through the PowerPoint that I did for the lesson, and the achieved objective was to recall what entropy is a measure of. Then you had to decide if a reaction would be spontaneous or not, which is the most that you'll get asked in an exam question. And then for excellence, if you can explain why a reaction can be spontaneous even though it's endothermic. So let's just scroll on to the next slide. There's a couple of definitions we make here. Now I got you guys to start by doing a little experiment, and it was simply to dissolve ammonium nitrate in water and to record the drop in temperature. And the point we were trying to make here was that although a reaction may be endothermic, there can be an increase in entropy. So just ignore that. So we did the experiment, and what you found was that, I'll just jump in here for a second to this page. So what we found was that when we took our ammonium nitrate, NH4NO3, we put that into water, a beaker, we found that the temperature dropped. Okay, so this was a positive enthalpy change, an endothermic reaction. Yet we know that there's an increase in entropy here, and the symbol for entropy is S, and we knew that the change in entropy was positive here. So we had a positive change in entropy and a positive enthalpy, and yet the reaction was spontaneous. And the reason the reaction was spontaneous was because we went from ammonium nitrate crystal, which is a highly ordered state, into aqueous ammonia, or aqueous ammonium nitrate, where all the particles are separated out. So there's an increase in disorder of the system. Particles are all nicely ordered in a crystal. So this first opening dart or experiment was just to exemplify the fact that although a reaction may be endothermic and appear to be non-spontaneous, that is not always the case. And that was just why we introduced that at the start. If we go back to the presentation, we gave the definition for, well, we looked at two different types of reactions. We looked at the first situation, which was the methane bubbles experiment that I used to introduce the thermochemical concept. With this particular reaction, methane plus 2 moles of oxygen going to 1 mole of CO2 and 2 of water. If we just pretend that we're dealing with molecules in this case for now, you have 3 molecules here on the left-hand side, 2 oxygen and 1 methane. That makes 3 altogether. But you also have 3 on the right, so there's no apparent increase in entropy there. But the reaction is exothermic and spontaneous. So in general, an exothermic reaction is spontaneous. There's so much heat given off that it's clear that the system wasn't very stable to start with. This is our ammonium nitrate situation. And this was an endothermic reaction, but there was an increase in entropy here. And that's not evident from the equation other than if you look at the state symbols. So you have to look at state symbols as well when you're trying to determine if there's an increase in entropy. And we go from a solid to an aqueous situation, so there's definitely a disturbance and a disorder of the particles, so an increase in entropy. But the reaction is endothermic, so when the take-home message is, when deciding if a reaction is spontaneous or not, you need to consider both the change in enthalpy and the change in entropy. It's not enough to just say the reaction was exothermic, therefore spontaneous, or vice versa, the reaction was endothermic, therefore non-spontaneous. It's not enough to say that. So what sort of questions will you be asked in an exam paper? Well, this is just a quick definition of entropy again. So the symbol for entropy is S, capital S in italics. It's a measure of the disorder of particles in a system, where these particles can be ions, atoms, or molecules. If you get an increase in entropy, then this is considered a spontaneous reaction, whereas a decrease in entropy is a non-spontaneous reaction. In other words, in nature, in real life, a disordered system will not rearrange itself into a nice ordered system naturally by itself, spontaneously. It just doesn't happen. And if you think about it, even if you think about your room, if your bedroom is in a mess, in a very disordered state, it's not just going to spontaneously reorder itself. It just doesn't happen, unfortunately. So you have to get up and start putting your shoes back where they're supposed to be, fold your clothes and reorder everything. So that's what they mean by that. Then we just look at some examples. Now, if we take these 4 questions here, and I've copied this page into my PDF annotator so we can write some answers for this. So we're looking at these 4 questions. I'll just zoom in a bit. Okay, so the first question here, we have to predict the sign of the entropy changes for the following, and basically decide if this is spontaneous or not. So a drop of food coloring diffuses in water. So we'll try and draw a little picture for each one. So what we're doing here is we have a drop of food coloring. Let's color it in, might as well. So it's red food coloring. Alright, and as we can see, the particles would be quite close together in that case. So liquid particle diagrams, your science, I'm drawing particle diagram. The particles in the liquid are not quite separated, they're just touching loosely. And that's the situation after we drop it. And then we're saying that we put that into water. Alright, and as we can imagine, the droplets start to diffuse out in the water. So you can see that the particle situation now is that they're further apart, and therefore there's a positive change in entropy, so therefore this reaction would be spontaneous. So hopefully that's easy to see. Now let's look at the next question. A lake freezes in winter, so what we have here is we're going from a liquid situation to a solid. So it's a liquid situation to a solid. So we're going from a disordered state, like I was saying before, an ordered state. Particles in a solid are regularly arranged, all touching, closely packed together, like so. Okay, so this is a situation where, like in the bedroom we were just talking about, if your bedroom was in a mess, it's not going to just magically or spontaneously reorder itself like that. So that would be a negative delta S, and that would be non-spontaneous. So freezing is a non-spontaneous reaction. Next example, puddle of water evaporates. So in this case, we're going from a liquid to a gas, liquid water, particles, water molecules, and loosely packed or liquid situation. But when you go to a gas, those particles don't even touch. Okay, so that is definitely an increase in disorder or entropy, and that would be spontaneous. And then just to look at a specific chemical equation, magnesium combines with oxygen to form magnesium oxide. So you have to be able to write these simple equations. Magnesium plus oxygen to magnesium oxide. It's a classic demonstration you've probably seen in junior science. Now, we need to talk about particles again here. So what we have is we have one magnesium particle, or 1 mole of those particles. We have an oxygen molecule. Okay, so let's just represent it like that. And then we're going to magnesium oxide, which is just 1 big particle, magnesium with 2 oxygens stuck in it. So as you can see here, we're going from 2 particles, if we just deal in particles for simplicity's sake, to 1 particle. So that is a decrease in entropy, which is non-spontaneous. And if you recall how this experiment was actually performed in our junior science, it takes a lot of heat from a Bunsen burner to get the magnesium to glow really brightly and form magnesium oxide. So it's actually a non-spontaneous reaction because you're going from 2 particles down to 1. So that's a decrease in disorder, and as a result, it's non-spontaneous. So now entropy it's a whole other story. You could teach probably 6 weeks on the concept of entropy. The only reason I can see why it's been included on the course this year is because there's students probably going from high school into university chemistry and they have no concept of entropy, and then suddenly lecturers are introducing the concept and teaching it. So it's probably just to give you guys a little starter, and it's not that much to just learn 1 lesson, but your questions should be pretty straightforward. So that is the structure, bonding and thermochemistry course finished. Next course we're going to have to cover will be organic chemistry, so we'll do a series of videos on that. But any questions, please just post them in the comment section.